right, welcome back to our word problems, our applications. Excuse me. We're going to next do number 20 in this book. It's a mixture type problem. It says, Bill Charlson needs 10% hydrochloric acid for a chemistry experiment. So he needs some kind of solution that's 10% hydrochloric acid and 90% something else. How much 5% acid, so that he has a solution that's 5% acid and 95% whatever else, should he mix with 60 milliliters of 20% acid? So he has a 60 milliliter solution where 20% of that is acid, and he wants to obtain that 10% solution. So we have a mixture problem. He's going to mix something that's 5% acid with something that's 20% acid to obtain a solution that's 10% acid. And you're trying to figure out how much he has to mix of the 5% acid with 60 milliliters of 20% acid to get his 10%. So let's do it. All right, I like drawing little pictures. Some people do charts, and if you have a chart way of doing it, that's fine. I like drawing pictures, whatever method if you have a method you're comfortable with, go for it. If not, you can go with what I'm doing. All right, so again, I'm no artiste, but let's say he's got this beaker here. And that beaker, we don't know how much is in it. So I'm going to go ahead and say that's X milliliters. But we know that whatever's in it, 5% has a concentration of 5% acid. And then he's going to pour that together with another beaker. This one we do know has 60 milliliters. And we do know that the concentration is 20% acid. And he's going to mix those together. So the two of them added together have to equal. We're not sure how much yet. I'll just go ahead and say Y milliliters. I'm not sure how much is going to be in there. But we know that that concentration has to be 10% acid. Okay, so far we have an equation. X milliliters plus 60 milliliters equals Y milliliters. And that's just from the amounts that are in the beaker. But we also have that the first one has a concentration of 5% acid. So 5% of whatever's in there is acid. So if you take 0.05 for 5% times the X milliliters, that would tell you how much acid's actually in that solution. So we don't know what the milliliters are yet, so we just say X. And then over here, 20% acid, if we take 20% or 0.20 times the 60 milliliters, that'll tell us exactly how much acid's in there. So apparently that one has 12 milliliters of acid in it. And then the other 48 milliliters are something else. And then down here, 10% of Y. 10% acid, so 0.10 times Y milliliters. So the amount of acid in the first solution plus the amount of acid in the second solution will have to equal the amount of acid in the mix. So this gives us another equation to work with. 0.05x plus 12 equals 0.10y. Well, I can use substitution here. I know that y equals x plus 60. So I can say, well, 0.05x plus 12 equals 0.10 times x plus 60. And by doing that substitution, I can make sure I have one equation with one unknown, one variable. And then that's not too bad to solve. Solve for x. 0.05x plus 12 equals, I'm going to distribute the 0.1, 0.10x plus, and 0.10 times 60 will give you 6. Subtract 6 from both sides, Subtract 0.05x from both sides. So I get 6 equals 0.05x. So divide both sides by 0.05. I'm going to get the x equals 120. So he's going to need 120 milliliters of the first solution to mix with 60 milliliters of the second solution to get your final result. If you do a real quick check, well, 5% of 120 is 6. 20% of 60 is 12. And then 10% of 180 is 18. And when you add these two together, 6 and 12, that equals 18. So the numbers work. You can do a quick check that way and make sure the numbers work. And they do. All right, next one. Number 34 in this book. So it looks like I need to go to the next page. This, if you go down, scroll down, bottom here, it says, in these exercises, express the cost C as a function of X, where X represents the number of items as described. Express the revenue R as a function of X. Determine analytically the value of X for which revenue equals cost. Then graph y sub 1 equals the cost function and y sub 2 equals the revenue function on the same xy axes and interpret the graphs. So we'll do A, B, and C analytically. So we're going to write it out on paper, and then we'll do D on the graphing calculator. All right, and we're looking at number 34. A technician runs a copying service in his home. He paid $3,500 for the copier and a lifetime service contract. Each sheet of paper costs 1 cent, and he gets paid 5 cents per copy. Let X be the number of copies he makes. So each sheet of paper he uses is X, like the number of sheets of paper he uses is X, whether you're talking about the cost of them or whether you're talking about getting paid per copy. All right, so let's set up a cost function first. So this technician, the cost function, oh, sorry, I didn't do this yet. The cost function has to deal with the cost of the copier. Remember that he had to pay for the copier in the lifetime service contract, plus the cost of his sheets of paper he's buying. So the cost function, we use C of X to name that function. C is the name of the function, X is the independent variable. The copier in lifetime contract was $3,500. So that's an initial upfront fixed cost that he has to pay. Then as he makes copies, every sheet of paper he uses, he has to pay 1 cent. So we take 1 cent times X, because we're going to let X represent the number of sheets, number of paper sheets. Or when we get to the revenue, it'll be the numbers of copies. All right, so that's part A, that's the cost function. Then when he goes to make some money, he's going to make his money by making copies for people. And for each copy he makes, he's going to bring in 5 cents. So 5 cents, 0.05 times X copies will tell you how much money he's bringing in. He's hoping to bring in more than his cost. He's hoping the revenue function comes out better than the cost function. Then he'll be turning a profit. If the revenue is coming out less than cost, he's losing money. If they come out equal, he breaks even. If revenue comes out more, then he's in good shape. So this problem wanted us to figure out, where does he break even? Where does the R of X equal C of X? Where does revenue equal cost? So we're looking at break even there. So you take the revenue function, the 0.05x, set that equal to the cost function, the 3,500 plus 0.01x, and then solve for x. Subtract the 0.01x from both sides. Then divide both sides by 0.04. And you get 87,500. So he needs to make 87,500 copies in order to break even. All right, let's check this out on the calculator. Let's put the 3,500 plus 0.01x in for y1, and let's put the 0.05x in for y2. And when you hit graph, you're going to see that you don't really see anything on there as far as intersections because the numbers are so big. Remember, the answer was 87,500. So let's go to our window, and let's just go ahead and let x min be 0, and let's let x max be 100,000. And let's go ahead and let the scale be 10,000. So that means that for every little tick mark on the graph, on the x-axis, it represents 10,000. And then let's let the y min just be 0. Let's let the y max. For now, let's go ahead and make it 100,000. Well, what happens to y when I plug that in? I think we can just let y max be 5,000. And I think we can just go ahead and say the scale is 1,000. And then hit graph. And there's my intersection right there. So second trace, let me calculate intersection, number 5. Okay, cursor's blinking on one of the lines, so I'll go ahead and hit enter. Cursor's now blinking on the other line, so I'll go ahead and hit enter, and then enter to guess. And it's telling me the intersection, the x value for the intersection is 87,500, which does not surprise me in the least because I figured out that the break even, or where they equal, was 87,500. And that's where the two graphs intersect each other. So that's what it looks like graphically. All right, 2 more problems. I guess I need to end show for a second. Next problem is number 44 in this book, and that's on the next page. Strength of a beam. The maximum load that a horizontal beam can carry is directly proportional to its width. If a beam 1.5 inches wide can support a load of 250 pounds, find the load that a beam of the same type can support if its width is 3.5 inches. What is the constant of variation? All right, so we have a direct variation problem. As soon as you see directly proportional to or varies directly as, you know you have a direct variation question. They're saying that the load, the maximum load, is directly proportional to its width. Then we get the scenario that a beam 1.5 inches wide can support a load of 250 pounds. So we need to use that scenario to help us find our constant of variation. Then once we know our constant of variation, we can then find the load that a beam of the same type can support if its width is 3.5 inches. Okay, so we have two questions we really have to answer here. Finding the load and finding the constant of variation. All right. Remember, for directly proportional to or for direct variation problems, so you might also see the proportional prop in there. For those problems, you have y equals k times x. Y varies directly as x, or y is proportional to x. Oops. Okay, I need the eraser. That's going to bug me right there. Woo. Okay, so y varies directly as x, and you could also say y is proportional to x, and it'll mean the same thing. So in this one, for the beam, the load the beam can carry is directly proportional to the width of the beam. So I'm going to make a little equation of L equals K times W, where K is your constant of variation. All right, so in this one they said a beam that can carry that load of 250 So we're talking about a load of 250 pounds. That beam has a width of 1.5 inches. Okay, so knowing that, we can plug in those pieces of information into the equation and solve for K. Figure out what constant of variation is. So divide both sides by 1.5, and you get that K, or the constant of variation, is 166 2/3. So now you can rewrite your equation with the actual constant of variation in there. You can say, well, L, or the load, equals 166 2/3 times the width, or W. And then it says, well, what about a beam that's 3.5 inches wide? What kind of load can that beam carry? Well, just multiply that width times 166 2/3, that constant, and you will get 583 1/3. And they've given us those loads in pounds. Now you've answered both questions. So the maximum load for the 3.5 inch beam was 583 1/3 pounds. Better not go over that. Might be in some trouble. All right, one more. Let's pull up the book and let's look at number 48. Height of a street light. A person 66 inches tall is standing 15 feet from a street light. If the person casts a shadow 84 inches long, how tall is the street light? I actually did a problem like this my first day of physics class in college, where we had the campus. I went to Florida Southern College, and the campus had a bell tower, has a bell tower in the center, and we had to go out and figure out how tall the bell tower was without climbing it and dropping a ruler down it. So we had to use techniques kind of like this. So let's see, how is this done? Person is 66 inches tall. They're talking about them standing 15 feet. So I'm going to need to do a little converting here, I think. Oh, yeah. The person casts a shadow that's 84 inches long. So I went ahead and converted everything to inches when I did the problem. And then I saw that the answer key had it in feet, so then I converted it back to feet. So that's what I'm going to do here too. All right, so we're talking about a 66-inch tall person. So this person is 5 foot 6 inches tall, standing 15 feet from a street light. Their shadow is 84 inches long. So their shadow is 7 feet long. So I mean, you can do everything in feet if you want, but with that 5 feet 6 inches, it kind of gets a little awkward. Well, you can say 5.5 feet, I guess. So. All right, but I did everything in inches, so that's what I'm going to do here. Okie dokie. So we have a street light. It's glowing. Okay. We don't know how tall it is, so I'll say X. And I'm going to do this in inches. We have a person standing over here near the street light. This person is 66 inches tall. And as the light is shining down on this person, the person blocks the flow of these beams of light so that they end up casting a shadow. And that shadow is 84 inches. They tell us that the person is standing 15 feet from the light post, which you do 15 feet times 12 inches per foot, you get 180 inches. What I really have here are similar figures. I first had the scenario with the lamppost. If you were just looking at like the sun coming down and the lamppost casting a shadow, this right here would be the 15 feet the person's standing from it plus the 84 inches there. So you really have a total of 264 inches for the lamppost shadow. And then for the person, you know, that person is 66 inches tall and is casting a shadow of 84 inches. We're going to assume the lamppost and the person are standing straight up and down. So that gives us two right triangles. The angle of the light coming down is the same. And then the angle, the shadow hits the ground and at the end there is the same. Like if those light if let's say the sun's up here and you're looking at sun's rays coming down, if that ray was able to keep coming down, and right here is the same angle regardless of whether you're talking about the lamppost or the person. So our corresponding angles are the same, which tells us that these two triangles are similar. Their sides are proportional. So we can set up a proportion to help us to find the missing measurement. We can say lamppost height over lamppost shadow equals person height over person shadow. We can do the whole cross multiplying. Remember, we're solving proportions, a little shortcut. Cross multiply equals cross multiply. So you have solve for x. Multiply 66 and 264, you get 17,424. Then divide both sides by 84. And you get this long decimal. And that's inches. And then divide by 12 inches. Again, since that's a decimal, it's actually an approximation. So little squiggly equals means approximately. Divide by 12 inches, and you'll get roughly how many feet. It's a rounded decimal, that's why I put the approximate symbol. And then your book just goes ahead and rounds it to tenths place. So they say roughly 17.3 feet. So that's about how tall the lamppost is. Okay, so that's using similar figures. All right, so that's all the examples I want to show you for this section. That should be enough to help you to see how to do all the problems that you're assigned in the application section. Have fun. Make sure you do as many problems as you can just to make sure you have this down solid. And of course, as usual, if you have any questions, don't hesitate to ask. Thank you for joining me.